All right, today's topic, atomic mass. Now, when we look on the periodic table, of course, we find the symbol for an element and its atomic number, which is the number of protons. But the other number, which will have a couple of decimal places, that's the atomic mass. So how do we calculate that number, and how do we get the data to calculate that number? Recall that the mass of one proton is approximately the mass of a neutron. From your notes last time, you wrote down the actual amounts in grams, and you can see that a neutron is ever so slightly more massive than a proton. Scientists have defined a unit that is the average mass of these two nucleons, called the atomic mass unit, or AMUs. In recent years, it's been abbreviated even further to just U, so sometimes you'll just see U. Where 1 AMU is equal to 1/12 the mass of the carbon-12 isotope. Now that's a real important definition to remember. Now why carbon-12? Well, it's unique in that it's very common and it has exactly 6 protons and 6 neutrons. So if you add them together and divide by 12, you would get the average mass of a proton and a neutron, or another way of saying it is that we would get the mass of a nucleon. All atomic masses are now based on this definition. Side note, in 1961, carbon-12 became the official isotope to use. Before this, oxygen-16 was used, where 1 AMU was equal to 1/16 the mass of the oxygen-16 isotope. Now, oxygen is atomic number 8, so you would have 8 protons and 8 neutrons, divided by 16 to give you the definition of 1 AMU. Question, did this change the actual mass of an AMU, going from oxygen-16 to carbon-12? And the answer is no. It's just two different ways of doing the same thing. Remember, what we're interested in is just the average mass between protons and neutrons. So if you had one proton and one neutron, divide by 2, you'd get an AMU. The only difference is that we're using another substance to do it. Now, carbon-12 is just a little easier to deal with. It's a solid. Again, it's very, very abundant, very common. So in 1961, they moved from oxygen-16 definition to carbon-12 definition. So how is atomic mass calculated? So how do we get that 39.10 for potassium? Well, you might remember last time we looked at 3 different isotopes of potassium. The first here has 20 neutrons, then 21, then 22. So how do we get that number? Well, you might think that we just add the 3 together and divide by 3. Well, that doesn't take into account that some of the isotopes are much more abundant than others. So what we use is called a weighted average calculation. Atomic mass is a weighted average calculation. Now, last year you saw it written like this, which is kind of a more expanded way of looking at it. And it just means that you're going to take the percent of something times it's the amount that you're interested in, percent times amount. This is just a cleaner way of representing that. If you haven't seen this symbol before, this is the Greek letter sigma, which means to sum. And so percent times amount, on and on, depending upon how many different percentages you have. Example, what would be a student's weighted average grade based on the following scores? So let's look at a case like our class, where 80% of your grade is based on tests and quizzes and 20% everything else. So let's say that out of the 700 points possible, a student scored 582 points, and out of 200 points possible for homework, 184. So to do a weighted average calculation, we would take percent times amount plus percent times amount. Now, when you multiply by percent, remember that you need to convert it into a decimal by moving the decimal place over 2 places to the left. So 80% becomes 0.800, 20% 0.200. And this would give us 0.84, which is 84.9%. For atomic mass, we'll be looking at isotopes, where we have a percent abundance and a mass for each one of the isotopes. So let's do a practice problem. Use the data below to calculate the atomic mass for magnesium. So here we have 3 isotopes of magnesium, and they have different percent abundances. Now what that means is if I had a sample of magnesium, and it would be magnesium anywhere, it would always consist of 78.7% magnesium 24, 10.13% 25, and 11.17 26. So that is that's a constant amount. So when we do this, we're going to be using the mass number to represent the mass of the isotope. So magnesium 24 has 12 protons and 12 neutrons. 25 has 12 protons, 13 neutrons. 26 has 12 protons, 14 neutrons. So we can just use the atomic mass number for the mass. When we do this calculation, remember, we need to convert the percent into a decimal. So it'd be 0.7870 times 24 plus 0.1013 times 25 plus 0.1117 times 26. Now, when you type this into your calculator, and go get your calculator if you don't have it, pause the video, go get the calculator, come back. All right, now when you type this into your calculator, you want to do it in just one go. Sometimes students will stop and do each one of these multiplications separately and write down the answer for each one. And they're really setting themselves up to make a mistake. So please follow my lead here. I'll tell you exactly what to do. So on your calculator, you'll type in 0.7870 times 24. You don't need parentheses. Plus 0.1013 times 25 plus 0.1117 times 26. And then hit equals, and you should get 24.31. Now, I can't tell you the number of times I'll see students that I'll have the work set up perfect, but get the wrong answer. And of course, they're just typing it into their calculator incorrectly. So please practice that a little bit. Make sure that you can get that answer. And please do not do multiple calculations to do this. It should be just as easy as I said. So this times this times this, plus this times this, and just hit the equal sign once. Now, when you do these type of calculations, I'm always going to be honest with you and give you actual elements. So when you come up with the atomic mass of an element, and it might be an unknown element, it'll always be found on the periodic table. So to check this answer, all we would need to do is look on the periodic table and see, is that the atomic mass for magnesium? And lo and behold, it is 24.31, so it is correct. For an element, a mass spectrometer is used to separate its isotopes and to determine the mass and percent abundance of each. So this is a mass spectrometer. And we're going to spend the next few minutes talking about a mass spectrometer and its parts. And I'm going to show you a video here in a second. Now, a mass spectrometer has 5 parts to it. The first thing we're going to do is take a sample, in this case an element, heat it up to have it become a vapor, so make it gaseous. Then we're going to fire electrons at it and cause each of the isotopes to become ions. So this is the ionizer. Now that it has a positive charge, because electrons have been removed, it will be accelerated towards negatively charged electric plates. And so it causes it to speed up. And then eventually it'll pass through a magnetic field that will deflect the isotopes differently depending upon their mass. Now, there are 5 stages to a mass spectrometer, and actually you can hold off on writing down these 5 steps until the next slide or a few slides when I define each one. But let's just kind of take a look at this mass spectrometer and see what each one of the steps are. So step 1 is vaporization. So that's taking place down here where we're heating the sample, causing it to become a vapor. Ionization, so we're going to fire an electron beam or electron gun at the isotopes, the individual isotopes, removing electrons. So it causes them to be positively charged. So hence the term ionization. It's turning them into ions. 3, acceleration. Now that the ions have a positive charge to it, they will be attracted to negative electric plates. And so they're pulled in this direction, and they're caused to go faster and faster. And then they're going to be passed through a magnetic field. The magnetic field will deflect their path depending upon their mass. And then detection. So we detect the isotopes as they strike our detector. And in this case, you can see that the sample has 3 different isotopes. Okay, we're going to watch a little video here.
Welcome to subtopic 2.2, the mass spectrometer. The mass spectrometer is a vital instrument in many kinds of chemical analysis. But how does it work? And how do we interpret the data that we get from it? A mass spectrometer works in 5 stages. First, the sample is vaporized. Then, it is ionized. Third, it is accelerated. Fourth, it is deflected. And fifth, it is detected. The deflection stage is the heart of the mass spectrometer. When we accelerate an ion, it would like to keep moving in a straight line. This tendency of the particle to move in a straight line, its momentum, is proportional to its mass. However, in a mass spectrometer, we use electromagnets to try to deflect the ions off their path. The amount of force that the ion feels from the electromagnet is proportional to its charge. The path that the ion actually takes is a result of its mass-charge ratio. A different particle with a different mass-charge ratio will take a different path. And this is what we are actually detecting, different mass-charge ratios. So let's analyze a sample. If we vaporize it and ionize it, accelerate it, deflect it, and then detect it, we can record its mass-charge ratio. If we repeat this with more of the same sample, we will record different size fragments. Eventually, we'll know the proportions of all the different size pieces in our original sample. So how do we interpret mass spectrometer data? Let's consider rubidium for an example. Here's some mass spectrometer data from a natural sample of rubidium. It tells us that 70% of this sample of rubidium was the rubidium-85 isotope, while the rest was the rubidium-87 isotope. If we multiply the percentages times their mass and add that up, then average that over 100 atoms, we'll find the average atomic mass of rubidium. Let's try the reverse. Let's calculate the relative abundances of boron-10 and boron-11 isotopes. First, let's imagine we had 100 of these boron atoms. Let's call the number of boron-10 atoms X. Then, the number of boron-11 atoms has to be 100 minus X. We can put this together to calculate the average atomic mass, which we already know for boron if we look at the periodic table. Do a little algebra, and it tells us that X is equal to 19, which is the percentage of boron-10, and therefore boron-11 has an abundance of 81%. That's it. Thank you for watching.
Okay, so now let's define each one of those steps of a mass spectrometer. 1. Vaporization. Sample is heated and vaporized, producing gaseous atoms. 2. Ionization. Atoms are bombarded by high-energy electrons, producing cations. So this step just literally removes electrons from the atoms, forcing them to become ions. Acceleration. The ions are accelerated within an electric field. 4. Deflection. Ions are passed through a magnetic field where the smaller the mass-charge ratio, and we'll talk about that in a minute, the more a cation is deflected. And 5. Detection. Ions with a specific mass-charge ratio hit a counter and are recorded. 2 factors determine how much a cation will be deflected in a mass spectrometer. Charge, and we use a lowercase c to represent charge. The greater the charge, the greater the deflection. And for mass, the smaller the mass, the greater the deflection. Now again, we're going to be using the mass number as the mass of an isotope. When comparing isotopes, use the ratio mass-charge ratio. The key idea is the smaller the ratio, the larger the deflection. So let's look at an example here. Imagine that you have two particles moving in a straight line. How will they be affected by a magnetic field? Well, the first one is larger, so more massive, and has a smaller charge. The second one is smaller, but has a larger charge. So the first one, as it goes through the magnetic field, will be deflected, in this case, deflected towards the magnetic field. But the smaller one is going to be deflected even more so, because it's easier to deflect something the smaller it is. And also it's easier to deflect something the greater the charge is. So either the greater charge or the smaller mass would cause it to be deflected more. So let's do some practice. For each set, circle the ion that would be the most deflected in a mass spectrometer. So we're given two bromine ions. First one is bromine 80, the second one is bromine 79. So our mass charge ratio for the first one would be 80 divided by 1, or 80. The second one would be 79 divided by 1, be 79. So this has a smaller mass charge ratio, so it would be deflected more in a mass spectrometer. For B, we have 80 divided by a positive 2, and that gives us the mass charge ratio of 40. And the second one would be 79 divided by 1, which would give us 79. So 40 is the smaller mass charge ratio, so that would be the one that would be more deflected in a mass spectrometer. Now for C, what you're looking at is the molecule bromine. And you might remember that bromine is a halogen, and all halogens are diatomic. So here, both bromine atoms that are in the molecule are bromine 79. And then one electron has been removed from the molecule to give it a positive 1 charge. So the only difference here is that we have two atoms, so we just need to add those masses together and then divide by the charge. So it'd be 158 divided by 1. So the mass charge ratio would be 158. For the second one here, be 81 plus 81, or 162 divided by a positive 2, which would be 81. So that's the smaller mass charge ratio. So it would be more deflected in a mass spectrometer.
All right, let's now look at what's called a mass spectrum. It provides the data needed to calculate atomic mass. So we have percent abundance versus the mass charge ratio for two isotopes of boron. Boron 11 is 80.1%, and boron 10, 19.9%. So we have the percent abundances, but we need the mass. And it kind of looks like that's not quite what you see down here because it's the mass charge ratio, not mass. However, we're always going to assume that Z is equal to positive 1, that 1 electron has been removed from these isotopes. Now, of course, as you've seen, you can remove 2 or 3, but for our purposes, for IB requirements, all we'll be looking at is Z equals 1, which makes it quite simple. So all you need to do is look at the mass number, and that is going to be the mass charge ratio. So we have everything we need to calculate the atomic mass. Percent times mass, percent times mass, adding them together. So let's look at that. So 80.1% times 11 and 19.9% times 10. Now remember, make sure you can plug this into your calculator correctly. So you might want to stop and see if you're getting the right answer here. And you should get 10.80 AMUs. On the periodic table, it's actually 10.81, but from the data that we're given here, it's 10.80. And in fact, the percent would be many more decimal places. So we're just kind of simplifying it a little bit. Okay.
Now let's go in the opposite direction. Percent abundance can also be found by using the atomic mass of an element. So let's do a practice problem. Chlorine has two isotopes, chlorine 35 and chlorine 37. Use the periodic table to calculate the percent abundance for each. So if you look on the periodic table, you find that the atomic mass for chlorine is 35.45. So we now are going to be able to calculate the percent abundance for each of these isotopes. And to do that, we just need to set up a little algebraic equation. Here we're letting X represent the percent abundance for chlorine-35, and 1 minus X would represent the percent abundance for chlorine-37. Now remember that the percentages are converted into decimal numbered. So if this was 20%, we would write 0.2. And so the 1 here is like 100%. So let's say if this was 20%, then 100 minus 20% would give us 80, and so this would be 0.8. Okay, now we need to kind of clean this up a little bit. So 35x, and then distributing the 37, so we'd have 37 minus 37x is equal to 35.45. And then we can combine like terms. 35x minus 37x gives us a negative 2x, and subtract 37 from each side gives us a negative 1.55. Divide both sides by negative 2, and we get 0.775. Now remember, X represents the percent abundance of chlorine-35, so we can say that chlorine-35's percent abundance is 77.5%. For the chlorine-37, we would just need to subtract 77.5 from 100 to give us 22.5%. Now, when you're done doing this calculation, I encourage you to go back to your algebraic equation and plug in the values that you just figured out and double check, make sure that it does give you the number you're interested in, or the atomic mass. So this again would be 0.775, this would be 0.225. If we were to plug those numbers in over here, you would get 35.45. It's a good way of double checking your work. Okay, that's it for today's notes.